In this video, we're going to talk about the first minerals in the history of the universe, those that are created in the expanding envelope of gas around a supernova. The first star may well have gone supernova. It might not have. It might have just collapsed into a black hole, and we're going to discuss that in a coming video. But even if the first star didn't go supernova, one of the first did. And when it did, the rest of the elements above iron, were created in the expanding envelope. And as had been true for the expanding universe for the entirety of time until now, this local expanding envelope is decreasing in temperature and thinning out as it takes up a larger and larger space. As the temperature decreased to reach 4,000 Kelvin, the first mineral in the history of the universe was formed. The first mineral was soon followed by 11 others, making the 12 minerals. Here meaning original, and it's borrowed from the ancient Mesopotamian city of that name, which was one of the earliest cities in Earth's first civilization. Let's jump back to the minerals. That first mineral to form was diamond. In order to be a mineral, you need to undergo a particular form of atomic bonding. You need to bind in a crystalline structure, and the entirety of your crystal, as you build, needs to be just a repetition of that crystalline structure. It needs to be crystalline as opposed to a more chaotic distribution, such as what you find in materials such as glasses and plastics. And the last thing you need is a relatively precise atomic structure. What I mean by relatively is that the atomic structure needs to be known, but there are different places in the atomic structure that might allow for different types of atoms to fill that place. So it has to be a relatively known structure. We know 3 of a certain type of atom go here, let's say, and then 2 oxygens go here and 2 nitrogens go here. And all you need to make a mineral is having the right atoms in the right place, the right temperature, with enough time. And so what we're looking when we're looking at this expanding envelope is what atoms are there in enough density that would form minerals with their neighbors and at what temperatures. So let's take a closer look. The first mineral in the history of the universe was diamond. It's the mineral whose bonds are hardest to break, and therefore the mineral which bonds at the highest temperature. It's made out of pure carbon, which is abundant in the envelope of supernovae. Following diamond was another pure carbon-based mineral, and that was graphite, which condensed at about 3,500 Kelvin. And as the temperature decreased to about 3,000 Kelvin, 4 other minerals were formed. There was cohenite, whose chemical composition is 3 iron atoms for every carbon atom. There was moissanite, whose composition is 1 silicon atom for every carbon atom. And then there was nearite, with a composition of 3 silicon atoms for every 4 nitrogen atoms. And finally, osbornite, made out of 1 titanium atom for 1 nitrogen atom. Then came the oxygen-based atoms. Hibonite, with 1 calcium, 12 aluminum, and 19 oxygen. That formed at around 2200 Kelvin, and that was followed shortly by spinel at 2130 Kelvin, consisting of magnesium for every 2 aluminum for every 4 oxygen. Prior to reaching 2000 Kelvin, corundum, 2 aluminum for every 3 oxygen, was formed. And that was followed by forsterite as the universe traversed 1900 Kelvin. Forsterite's composition being 2 magnesium, 1 silicon atom, and 3 oxygen atoms. Then came rutile, whose composition is 1 titanium atom for every 2 oxygen atoms at 1840 Kelvin. And finally, at about 1800 Kelvin, came enstatite, 1 magnesium, 1 silicon, and 3 oxygens. With enstatite formed in the expanding envelope of our first supernovae, the first stage of mineral evolution has occurred for the first time in history. These same minerals would continue to be created by supernovae from then on. Beyond these 12, no minerals could form until we reach a later stage in history when the first star lights up that is surrounded by a gaseous nebula filled with heavier elements. If you like this video, like it. If you're into big history, definitely subscribe. And until next time.